Ternary diagrams contain three components, each located at the vertices of a triangular plot. As the temperature increases perpendicular to the plane of the diagram, the 3D image below is created. The ternary diagram can be thought of as three binaries combined. This is how we achieve the three binary eutectics, and in combination we obtain the ternary eutectic. Now, in order to read the ternary diagram, this 3D image approach would be very confusing. So to solve this problem, we transform it to a 2D approach. This is kind of similar to mapping mountains on a flat map. The 3D version here is the real-life system, but it's very hard to read. So we take the isotemp lines and map them onto a 2D plane. When mountain elevations are mapped to a 2D image, continuous heights are mapped. However, for the ternary system, we're going to map continuous isotherm temperatures. These temperatures are the points where crystallization occurs. The center line below is the boundary trough for the eutectic phase. To determine the composition, there are two methods that can be used. The first method consists of drawing parallel lines to the side opposite of the triangle. For example, if we were to look at iron, 100% iron would be this vertex, and 0% iron would be on this line. Parallel lines go across the page, and as you can see, it starts at 10% and ends at 100. The same is true for the chromium and nickel. For the second method of determining the composition of each component, a line is drawn from the opposite side through the point of interest and into the vertex. If we have a steel mill and we have a customer that is looking for stainless steel with compositions that is 60% iron, 28.5% nickel, and 11.5% chromium, and we need to find out what temperature will be needed to melt and obtain a steel at these compositions. To use the method of parallel lines approach, we would draw isocomposition lines parallel to the respective sides opposite of the triangle from each percentage of the component that we are working with. Our point of interest will be where all three lines intersect. This temperature is going to be the desired temperature in order to melt the steel. First, let's start with iron at 60%. Remembering that our composition will need to be 100%, and if we had 0% chromium, in turn we would have 40% nickel. By drawing an isocomposition line between the 60 and 40%, we will gain a parallel line from the opposite side of the triangle of iron. This would also be the case for our chromium. If we were at 11.5% chromium, and we think of this as a binary containing only chromium and iron, our composition of iron would be 88.5%. By constructing a line between these 2 points, we will obtain our parallel line opposite that of chromium. In the same manner, if we were to have 28.5% nickel, 0% iron, we would have the binary nickel and chromium. With 28.5% nickel, we would have 71.5% chromium. This gives us our third parallel line that is parallel opposite the side of nickel. Therefore, our temperature of interest, which we wish to construct, is where these three lines intersect. As you can see, we were slightly over 1410 degrees C. If we want the exact temperature, we'll take a perpendicular line in between these 2 points and interpolate. The distance between our two liquidus lines is 1 centimeter. And the distance between our point of intersection and the 1410 degrees mark is 0.2 centimeters. Therefore, in order to obtain the desired stainless steel, we will need to heat it to a temperature of 1412 degrees C. Now let's say that we have a stainless steel and we begin to heat it in order to determine the compositions. We find that it melts right here. To determine the amount of iron, chromium, and nickel present and gain the percentages, we will first draw a line from each vertex through our temperature that the melting occurred To determine the percentages of each component, we will start the side opposite of the triangle. In this case, iron would be at 0% here. So to determine the percent at this temperature, it will be this distance divided by the total distance. We have a total distance of 14.8. And the distance from the point of interest to the 0% line is going to be 4.6. This will give us 31% iron. The total distance from our chromium vertex to the other side will be 14.7. And the distance from 0% chromium to our point of interest is going to be 3.8. This is going to give us 25.8% chromium. Our total distance from the nickel vertex to the other side of the triangle is going to be 14.8. And we have 6.5 centimeters. This is going to give us 43.9% nickel.